A modern vehicle contains between 50 and 100 individual electronic control units. If every one of these modules required a direct, point-to-point physical copper connection to every other module, the resulting wiring harness would add hundreds of dead weight, drastically reducing fuel efficiency. Engineering teams solve this by using a shared bus network. This architecture allows thousands of individual wires to be collapsed into a single, streamlined communication line where modules broadcast and receive data along a common path. At the foundation of this hierarchy is the Local Interconnect Network, or LIN. Operating at slow speeds between 9.6 and 19.2 kilobits per second, LIN is the equivalent of a simple text message. It's a low-cost solution reserved for non-critical comfort features like power windows, mirrors, or interior lighting. While single-wire networks like LIN save significant cost and weight, their low data rates are insufficient for the powertrain. In systems where a delay of a few noseconds can compromise safety, the vehicle requires a more robust architecture. For systems like the engine ECU and ABS, the vehicle shifts to the Controller Area Network, or CAN bus. If LIN is a text message, the CAN bus is a reliable, high-speed phone call, ensuring constant communication across the powertrain at 500 kilobits per second. Reliability is achieved through differential voltage. By mirroring a 3.5-volt signal on the CAN high line with a 1.5-volt signal on the CAN low line, the system filters electrical interference. The computer calculates the difference, effectively ignoring background noise. As EV battery management systems became more complex, standard CAN reached its limit, leading to CAN FD. This protocol functions like a broadband video call, pushing 5 megabits per second for EV data loads. These higher data speeds introduce a physical challenge: signal reflection. Without precise management, high-speed electrical pulses hit the end of the wire and bounce back, creating data collisions that can crash the entire network. To prevent these reflections, engineers install termination resistors at the extreme ends of the bus. These resistors act as a terminal runway, absorbing the high-speed electrical signals so they cannot echo back across the copper lines. In a healthy CAN network, you will find two 120-ohm resistors wired in parallel. Because electricity flows through parallel paths, total measured resistance is half of a single resistor, exactly 60 ohms. Faster flex-ray networks for steering use 90-ohm resistors. Using that same math, calculate a healthy flex-ray reading. The correct value is 45 ohms. Mastering this math is the key to verifying a network's physical integrity. It allows you to confirm if a circuit is intact or compromised without having to physically disassemble the vehicle's interior. Before applying a multimeter to these data lines, the vehicle's ignition must be completely off and the modules fully powered down. Probing an active network with an ohmmeter pushes external voltage into your tool, which can destroy the multimeter or damage the transceivers inside the ECUs. These resistance readings provide a map of the failure. A reading of 60 ohms confirms a healthy circuit. If you see 120 ohms, the network has an open or a missing module, as the meter only detects one resistor. A reading of 0 ohms indicates a short circuit, meaning the two communication wires are physically touching. Beyond copper-based CAN systems, we reach the high-speed frontier. The MOST protocol uses optical fiber for infotainment data, while automotive Ethernet serves as the high-speed backbone for ADAS cameras and over-the-air telematics. These systems abandon traditional resistance-based testing entirely. Automotive Ethernet utilizes single twisted pairs to achieve gigabit speeds, while MOST uses pulses of light, requiring specialized diagnostic tools that look for signal attenuation rather than ohms. Modern vehicle repair now requires a dual mastery of traditional electrical circuit testing and advanced IT-level network diagnostics. This table summarizes the speeds, mediums, and termination values for all 6 protocols. Take a screenshot for your next inspection. Let's verify. Single wire for mirrors? LIN. CAN bus resistance? 60 ohms. Light pulses? MOST. Twisted pairs? Noise cancellation. Flex-ray resistance? 45 ohms. If this guide helped you decode the vehicle nervous system, subscribe and share with your team.